Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our calculus series here, and we stopped last time at trying to find the Riemann sum, or in this case we call it a double Riemann sum, of a volume of a solid in 3D space. So just to briefly recap, what we did was we derived the Riemann sum, or in this case a double Riemann sum, to find the volume that's in between the quadric surface or the surface that was given, as well as its restricted domain. And so in this case, if we take this example here, we're trying to find the volume of all of these things. So that whole volume, right? So it's not just the quadric surface, but it's also the volume underneath that quadric surface all the way to this rectangle. And that's how we were introduced to double Riemann sums. And since we know that the limit of Riemann sums is an integral, so if we take the limit of a double Riemann sum, then that's basically a double integral, right? And this will give us the exact area, or not area in this case, volume, the exact volume of whatever surface we try to get its volume of. And so we went through an example of getting the Riemann sum of a surface, and we did it twice in the previous video. And you all know I hate doing that. I don't like Riemann sums, if I'm going to be honest. But it is a foundational concept for introduction to integrals. So I still think it's important in some ways, especially when we're trying to approximate stuff. Not all problems can be solved analytically. Sometimes we have to use numeric methods, and one of these methods would be approximating. And so we can use Riemann sums to do that. So it is still important, just not in this course, because here we're trying to solve everything analytically. So meaning there's an exact answer. That's the difference. Okay, so let's move on to a new topic, or not, no, scrap that, not a new topic. I meant a new concept, still the same chapter though. We're gonna go through the midpoint rule since I kind of touched on it a bit, but here we're gonna actually briefly discuss what it was and what it is now. So what it was previously, it was actually one of the methods we used for approximating single integrals. We have this idea of the midpoint rule, the trapezoidal rule, the Simpson's rule. And those were methods we used in calculating areas in 2D, in real valued functions in Calculus 2. And apparently in Calculus 3, they have counterparts. So they also have these things for double integrals. And so let's look at the midpoint for double integrals. So here, we actually use a double Riemann sum to approximate the double integral. We also pick a sample point, but in this case, it has to be the center of our region R sub ij. And so in other words, well, we have a midpoint of x, and we also have a midpoint of y. So let me just hop right into it, and I'm going to proceed with an example, just to get it over with. So the midpoint rule for double integrals, in this case, so here, let's look at one of them. So we have a double integral, then that's the R rectangle or region that we're looking at. Here we have a function of two variables with respect to its change in area is actually just approximately the double Riemann sum. So this is M starting from I is 1. This one's N starting from J is 1. And here, we actually get the midpoint. So here we get the midpoint. Oh, this is J. Change in area. And we're saying that, so what are these terms? This x sub I with the horizontal line is midpoint of this interval. So starting from xi minus 1 all the way to xi. So it's the midpoint of that interval. And similarly, y, which is also the midpoint of that interval. So in this case, it would be yj minus 1 all the way to yj, right? And so that's the rule, okay? Right. Let's do an example here. Example 3. So here we're going to use the midpoint rule with m and n equal to 2, and we want to estimate the value of the integral. Let me just write it out. So now let's apply the midpoint rule. And we're going to use m and n are both 2. And we're going to estimate the value of the integral. So it's going to be a double integral. And this is the function with 2 variables with respect to a. And we're going to look at what r is exactly. It's the rule that all points x, y, x is in between 0 and 2, y is in between 1 and 2. Right? So how do we go about a problem like this? Well, first of all, I would probably draw it in this case. So if we want to use the midpoint rule, we evaluate our function and the centers of the 4 subrectangles. So I would actually just draw this. So let me quickly do that. So here my x starts from 0 all the way to 2. My y starts from 1 all the way to 2. And so that's my rectangle. And it says we have my m and n, which are equal to 2. So I cut them both like that. So my n is this, or my j. Then my I is this. So the procedure here is to look at each of these boxes. That's my j moving. And then I'm going to look at these boxes. And that's my I moving. Okay? And then I divide these. So I'm going to be honest. I don't know how to divide this, basically. Anyway. Oh, wait a minute. Oh, my bad. This is actually supposed to go all the way here. Whoops. There we go. Because this is supposed to be 0. Right, and then this is 1, and then this is 1 plus 2 is 3, 3 halves, 1.5. Okay. And then we can finally do a midpoint here. So let's see, this is R11. This is R12. So my second index is the one moving. And now here I go R21, R22. So I had a hard time doing this previously, but now I figured out the pattern, finally. And then my blue dot, this is my midpoint. And then, okay, let's actually start solving it. So let's see. So this is the integral, or the double integral in this case, of my function of two variables with respect to a. And this is just, oh, I just realized I have no space. Let me go here. And so this is actually just equal to a double Riemann sum from I starting at 1 all the way to 2 in this case. So that's funny. This is all the way to 2. This is also all the way to 2. J starts at 1. And let me see. My function, right? Or in this case, it's actually my midpoint. So there's, how do I write this in a not weird way? Because I am gonna write it in a very, very, very weird way. Okay, I'm just gonna do I'm just gonna make it a function maybe. So it's this function of two variables. And then this is J. And then my change in A. So here in this case, my change in A, let's actually get this one down. So my change in A, or my change in area, what is that gonna be? Well, that's my change in X times my change in Y. And so this is gonna be this area here, which is 1, times this area here, which is 0.5. And so 1 times 1/2 is 1/2. That's my change in A, right? Okay, what else do we know? We want to, or what else do we want to determine? We want to determine what each of my points are here, right? So I actually have 1, 2, 3, 4 points. So I have x sub 1. Here, let's solve this. This is 1 point, or 1/2 actually. That's 1/2. And that means my corresponding y1 is actually just 1 plus 1.5. That's 2.5. Divide that by 2, and that's it. So in this case, that's 5/4, if I'm not. I basically get the thing in between here. Divide that by 2, 1.25. So yes, that's 5/4. Then I keep going. My x sub 2 is this one here. And so that's going to be 3/2. Then my y sub 2 in this case is going to be 7/4. And then I go from there, right? And so here I have this. Let me go ahead and approximate it. So I get 1/2 multiplied by my, well, each of these, right? So it's my f at this point, 1/2 5/4 plus f at, I think this was, I'm gonna go up then. So still x1, but this time y2. So 1/2 7/4. Then I go to my next x sub 2, so 3/2 5/4. So I should have like 4 combinations here, 7/4. There we go. And then I should get some values here. So I get something like 1/2 5/4. This is gonna give me negative of this. And then this one's going to give me negative 139 over 16. This one's going to give me 5, 1, 16. If I'm not doing my math wrong, or am I? Yeah, no, actually I shouldn't be. There's a triple here. There's a multiplier that makes the negative more dominant. Okay, I'm gonna trust that it's doing my thing correctly. So I have those four values. And I'm going to get something, I'm just gonna go to the final answer. It's negative 11.875. That's my answer. So that's the midpoint rule. And in some examples here, in the next couple of examples, we will see the exact value of the double integral. So we'll be able to go through solving the actual integral analytically. And remember that the interpretation of a double integral as a volume is valid only when our function f is positive. If it's not positive, then the integral is definitely not a volume. And it is similar in calculus too, since we also thought of positive real valued functions as the area under the curve. But the moment our function becomes negative or goes down to some other quadrants, maybe in 3 and 4, then we sort of treat it as a difference in areas. It's not the total area underneath the curve anymore, right? So I'm getting the idea it's going to be something like that. Something like that. Here, at least in calculus 3. If our function is not wholly positive, we might have to do some subtraction in volumes. Anyway, let's go ahead and look at this idea of iterated integrals, because I have actually a couple of examples here in my homework that I want to go over. So what are integrated integrals? Let's recall that it is usually difficult to evaluate single integrals directly from the definition of an integral. It is really, really difficult to evaluate a Riemann sum. However, the fundamental theorem of calculus provides a much easier method. So that's the cheat code provided by Newton. The evaluation of double integrals from first principles is even more difficult. But here we see how to express a double integral as an as an iterated integral. So maybe this is something that we do again and again, kind of thing. And from there, which we can then evaluate by calculating two single integrals. Let's go into the examples. So suppose that our function f is a function of two variables. We're going to say this function is integrable, and it's on the rectangle R with a domain or a bounds, AB by CD, so intervals. And so we have a notation, and we're saying x is fixed, and f of xy is integrated with respect to y. Okay, let me actually write this out. So we're going to create a scenario. Suppose our function f is integrable, meaning it can be integrated. I'm going to assume the function is continuous. Specifically on this rectangle, R, and it has that, right? It's within those two intervals. And so we go the integral of c to d of our double variable function. Now I'm making my own stuff. I mean a function of two variables, double variable function. And here what this means is that x is fixed. So x is fixed, and f of xy is integrated with respect to y. From y equals c to y equals d. So here we're saying what x is fixed, y is a variable. So here it's this idea of, so I thought of thinking about it as partial integrals, but apparently that's only for derivatives. So now I'm thinking about it in terms of integrals. Okay. And so we integrate y here. This procedure is called, oh, it's called partial integration. And it is similar to partial differentiation. Now that integral is a number that depends on the value of x, so it becomes a function of x. Wait, what does that mean? Okay, so this is a partial integration with respect to y, right? And so from there, now we see that this particular number, this definite integral, is actually just a number that depends on x. Depends on what that fixed constant is, right? So we're saying that this number depends on x, so we're saying a of x is just this integral. Right? And then what if we now integrate this function a from x equals a all the way to x equals b? So here what we did was we integrated with respect to y. So we will get something out of y, but then it will still depend on what our x is. Right? So this could be, I don't know, this could be, I'm thinking, this f of xy could be as simple as xy, right? And so if we integrate this, well, based on calculus 2 stuff, is we take this constant out. This y is going to be y squared over 2. And then from there, we now have this thing. Oh yeah, also we don't need to add the constant because it's a definite integral. Now we have that. But then again, it will depend on what our x value is. So if our x is 2, then this is just y squared. If our x is 1, then this is y squared over 2. Stuff like that, right? So that's what I mean. Now what happens? Here's the next thing. What happens if we integrate this a? So we integrate it from a to b. And here we do it with respect to x. So what's happening here? This is the same thing as integrating this integral, integrating this integral, right? With respect to x. So here you see how this is kind of like a double integral. And so the integral on the right side of equation 7 is called an iterated integral. Usually the brackets are omitted. So usually these brackets are omitted. Let me just go ahead and show what that would look like. It would look something like this. And now this is a double integral. Oh, okay. So here we put a dx here and then dy. Or I think the order doesn't matter. Oh, it doesn't. Why? Because of Clairaut's theorem. Clairaut's theorem, right? When we did partial integration, f sub xy is the same as f sub yx. When we did this. So here it really doesn't matter what the order is. We could integrate it with respect to x and then with respect to y. I think. Or am I just dumb? I think. Let me see. So here we first integrate with respect to x. Oh, my bad. Then we integrate the resulting function of y with respect to y. Whoops, my bad. So, whoops, sorry. I integrate first with respect to x, and then I integrate with respect to y. So that's how this would look like. I almost I almost said the wrong thing. Okay. And so the idea is that we work from inside out. So you know that movie Inside? Oh, anyway. So let's actually do some evaluating here. Let's get some practice doing this. So let's evaluate the following iterated integrals. Now I know why it's iterated because we integrate again and again. So let me do letter A. So this is 0, 3. What's this? 1, 2. Then we have x squared. Then we have y dy dx. So the first thing we want to focus on is integrating that inner integral. Once we get something out of that, then that's what we integrate next, right? So first we integrate this inner one. So we go 1 to x squared y dy. And here we treat x as a constant, right? So we did talk about doing that. So this is x squared. And then this is, I believe, y squared over 2 from 1 to 2. And then I get something like, yeah, so we get the antiderivative. This is x squared. This is 2 minus 1/2. And then that's just 4 over 2, 3/2. Oh, and then we get 3 of x squared, right? And then from there, now let's do the outer integral. So we have this number, right? Instead of the integral, we put the number instead, dx. Oh, and then we do x cubed over 3, 0 to 3, right? And then I think, oh, to make my life easier, I could do this. 1/2 x cubed. Done. Made my life easier. This is 3 times, or 3 to the power of 3, that's 27 halves. And that's my answer. Right? Yeah, it's just a shortcut. So yeah, so we integrated starting from the inner integral, and then we work our way outwards. So inside out. Okay. And oh, so funny enough, when we do B, right? So just fun fact, this is actually, I'm not gonna do it anymore because I already saw it. But if we switch the roles, so they actually gave a similar example here. So here we're gonna make this 1 and 2, right? Here we make this 0 and 3. We do the same thing, x squared y dx dy. We actually get the same thing, right? Here we integrate with respect to x first, and then we integrate with respect to y. But then again, our bounds have to switch. So that's the only difference. And this works because of Clairaut's theorem. Oh, so it's not Clairaut's theorem. Now it's someone again. It's Fubini's theorem. So it's very, very similar to Clairaut's theorem. Here we're saying it's Fubini. And who in the world is this guy? He's an Italian mathematician, Guido Fubini, who proved a very general version of this theorem in 1907. But the version for continuous functions was known to the French mathematician Augustin Louis almost a century later. He had a last name there, but I'm not going to say it because I know I'm not good at French. Okay, so Fubini's theorem states that if f is continuous, if our function of two variables is continuous on rectangle, we're going to say this is the set. Oops, don't know why I did that. This is the set of all points, and we're putting bounds. I don't know why I put x again. I meant y. This is y. D. If it's continuous in that rectangle, then we're saying it's double integral of my function with respect to its change in area is actually just the double integral of my function with respect to y first and then x, which is actually just the same thing if I switch these rows. But then I have to integrate it with respect to x first and then with respect to y. So this is Fubini's theorem, and it's very similar to Clairaut's theorem on partial derivatives. Right? Okay. Oops. Okay, now let's do a couple of exercises. We have a proof. I'm not gonna do that, mainly because I don't want to. Okay, we even have a couple of examples here with some stuff. Okay, let's go through some examples actually. We even have find the volume of a solid. That's pretty cool. Average value of a function. Ooh, did we talk about that? We did talk about average value of a function. We take its integral. And it's basically the mean value theorem for integrals, right? It's basically that. Okay, let me try and do some stuff here. Okay, so let me go ahead and do some exercises. So here we want to evaluate the double integral. And this double integral, we want to first identify it as a volume of a solid. Right? So our double integral is this with respect to its area. And we have r from 0, 1 by 0, 1. So how do we do that? Well, we can use what we learned right here. Fubini's theorem, kind of. We can turn it into, we can turn it into Fubini's theorem. F is continuous. Why? It's an elementary function. Specifically, it's a linear function. Every linear function, or honestly, every polynomial function that's elementary is always continuous. Trigonometric, polynomial, quadratic, cubic, logarithmic, exponential, all of those stuff. They're all. So here, let's actually make use of Fubini's theorem. So since our function of two variables, or actually, surprisingly enough, this is a one variable thing. Huh. Okay, we're saying since this thing is continuous on R, and I'm assuming it is, then we want, oops, not that. I don't want to deal with anything Riemann related right now. I want to focus on the analytical terms, the analytical tools that we can use. Then we say that this integral is just equal to 0, 1, 0, 1 of this function. Do we integrate it with respect to x first or with respect to y? In this case, it doesn't matter, right? Doesn't matter. Why is that? We could do dy dx first. We could do dx dy. It's the same thing, right? And now let's solve the iterated integral. Is it a number? Let me see. I feel like it is a number or something. Oh, shoot. Wait a minute. Oh, so I have to. Well, let me see. What's the answer though? Okay, apparently it's 3. Let me see if I can get that. Let's see. So so now we use this theorem. Now let's solve it, right? So here we first do this from 0 to 1 to here. So here I got 4y minus, and this is, I believe, 2y squared. Oh, but then if I integrate it, oh shoot. Wait a minute. Now that I think about it, I don't think this is possible. This is y squared. From 0 to 1. This is 4 minus 1. This is 3. Now if we integrate, oh, actually, no, it's not. No, no, no. And then I do this. 0, 1, 3. 3, 1, 0. Answer is 3. So it is possible. I didn't need to identify the volume of the thing. I just used what we know, and we know Fubini's theorem. And so we got the 3, right? Done. See if we pulled it off. That would be funny though. It is a theorem, so yes, we got it. Okay, let's do another one. So here we want to calculate iterated integral. And I already know I'm gonna copy paste this because there's a couple of examples. Oh shoot. Okay, that's not good. Okay. Life hack. So, oh, what's happening? So the integral is 1 to 2, 0 to 4, 6x squared y minus 4x. And then this is dy dx. So what is this? Let's first solve this integral. Whoops. So we're doing it in terms of y. Now, here x is a constant, so I'm going to leave it be. So I'm going to say this is 6x squared. This is y squared over 2, right? This is minus 4x. I leave that be. Or actually, in this case, since this is a number, I add a y there, right? This is from 0 to 4. And then I could simplify this even more. I could say this is 3x squared y squared minus 4xy. I could factor out an x. Or in this case, I don't need to actually. Then here I solve it. I plug all of these numbers for y. If I plug in the 0, everything's 0. If I plug in the 4, I get this is 16 times 3, that's what? It's 48x squared. This is minus 4 times 4, so minus 16x, right? And then from there, now I evaluate. Let me put a little check mark. Now I evaluate from 1 to 2, this time with respect to x of this thing, right? So that's how we evaluate double integrals. So now I can, this is just a normal integral. So I'm going to factor out a 16. So I get 1/2. This is 3 x squared minus x dx. Let me see. This is 16. This is 3 over 2 x squared. This is x squared over 2. Oh, actually, my bad. This is x cubed from 1 to 2. Right? And then from there, let's evaluate the whole thing. So this is 2 cubed, 8. 2 squared, 4 divided by 2. 2, 6. 8 minus 2, 6. Minus, this is 1. Minus 1/2. So that's 2 over 2, so that's 1/2. 6 minus 1/2. 2, 12, 11, half. 16, cancel 8. Is it 1? 1. 88. Right? So everything's just 88. That's the number. And of course, I'm gonna double check to see if I got it. I don't want to waste some mistakes here. Okay, we got 88. Okay, let's do it again. Number 4. Uh-oh. Oh, shoot. I did not mean to do that. I meant to do this. Nice. Okay, so what's the integral? Negative 5, 5, 0 by half. Our function y plus y squared cosine x. So a function of two variables here. This is dx, dy. So we first want to integrate with respect to x and then with respect to y. Let me do that first. So 0 by half y plus y squared x, cosine x, I mean, dx. What is this going to be? Well, here my y's are numbers. So I'm going to immediately integrate. So this is yx, y squared, that's a number. Cosine x, that's, we take its antiderivative, that's sine x. And there we have it. Now we plug in x to here. So if we make it 0, sine of 0 was that? 0. So if we make everything 0, that's just nothing. So here this is by half y plus y squared sine pi half, which is 1, right? Yes, so that's my number there. And then after doing that, let's do the outer integral. So from -5 to 5 of this thing with respect to y. And then we do it again. So this is pi half y squared over 2. So this is pi y squared 4. Pi fourth is, oh no, I cancel that. Then we have pi cube over 3. Holy, okay. And then we'll plug in all of the 5s. So we can say, okay, this is pi, 5 times 5, 25. 25 pi over 4 plus this is 5 cube. What's that? 125? I also don't like integrals. 20, okay, 125 divided by 3 is that thing. So that thing minus, oh, same thing. 25 pi fourth. This time we subtract that thing. And then what happens now? Notice here this gets canceled, right? 25 pi over 4 minus this. But here I added these two. So I got 2 times this. So I got 125 times 2. That's 250 over 3. And so that's my value. Or that's my answer, right? Let me see if we got it. If I messed something up, let me know, I guess. Or if there's a quicker way I could do it, please let me know as well. Let me see. Yeah, 250 over 3. Okay. Okay, so again, these are some calculus 2 stuff. The only difference is we're taking partials again. Partial integration, to be specific. Okay. Number 5. So again, we do the same thing. Whoops, I'll go there. Okay, so here let's do it again. 1 to 4, 1 to 2. And then this is our function of 2 variables, x over y over x, plus y over x. And we do dy dx. Let's first go through the inner integral. Dy. What I like to do here is I like to separate these things. When my x is a number, what's my y? And then when here, I have this. So when my x is a number, let's say 1 or 5 or something. This is actually, if we integrate it, this is x, ln y. And to be precise, this is the absolute value of y. Here we add, so we have 1 over x times y. So this is 1 over x, y squared over 2 when we integrate it. So this is just simply going to be y squared over 2x. Then we evaluate. So we plug all of these numbers in y. And so we get x ln 2. Is ln 2, is that a nice number? I don't think so. It's not. Plus, and I think this was 4 over 2x. And then I subtract that to when I plug in 1. ln 1 is 0, right? ln 1, yeah, that's 0, so that's nothing. Then I subtract it here. So this is 1 over 2x. Oh, look at that. I get x ln 2 plus 3 over 2x, right? And then now I integrate this in terms of x. So this is 1 all the way to 4 here. Now what is this thing? I could do it per term. So here, if I look at x ln 2, actually this is simple. This is ln 2, because ln 2 is a number. Natural log of 2, x squared divided by 2. So we could do something like this, right? And then this one is just 3 halves. 1 over x is ln of its absolute value. Then from there, let's see. I plug in my 4, I get 16 over 2. That's 8. So I get 8 ln 2. I added to 3 halves of ln 4. We don't know what that is. Okay. So I could say 3 ln 4. And then I do 1 here. So minus this ln 2 over 2 minus ln 1 is 0, so I don't need to include that. So that's my answer. It's not simplified, but it's something. See if we did get it though. I hope we got it. Oh shoot, it is some number. 21 over 2 ln 2. Can I simplify it nicely like that? Wait, let me see. Can't do that. Wait, it should give me the same number, right? What's this? Okay, it gives me like 7.278045396. What does this give me? Okay, 8 ln 2. I added to 3 ln 4. Or actually, I added to 3 ln 4. I divided by 2. And then I subtracted to ln 2 by 2. Okay, I got the same thing. I got the same thing. Would be nicer to simplify. But yeah, I get the same thing. Okay. So sometimes I can't simplify these things. I'm just gonna I mean, in an exam, they don't really care about it too much. It is better to make it simplified because it's nicer. But here I'm totally okay with not doing it. Yeah. I just wanted to know if I was on the right track. Okay, another one. We have a double integral here. Volume of solid questions. Oh, it's mostly volume of solid questions. And then iterated integrals. Okay. 0, 1, 0, 1. Six xy dy dx. And then again, we just integrate. Okay, this is going to be my last one because it's pretty much the same for all of them. So I'm not going to waste my time. Unless there's something really complicated, then that's just going to be super funny. Okay, so here, oh boy. Okay. This is an integration by parts. Question mark. So I have this 6x that I can completely take out. I guess that's one step of doing it. But then I have this x squared y squared. What else can I do? We do a trig thing here. Isn't this just one? Or no? If I make it make it trig. Hmm? Let's pretend this is some number, like 5 or something. What would be a way to do this? Oh God. How do I integrate a square root? Hmm. Let me think, let me think, let me think. I don't. How do I integrate what's inside a square root? I'm pretty sure I use a trig sub here. I am quite sure I use a trig sub, right? Let me double check, see. I just want to double check. I swear, I think this is a trig sub or something. Um, hmm. Yeah, it's tricky. Oh, so we do a U sub here, which is something I wasn't completely expecting. We could do a U sub. Yeah, let me do a U sub. So here I'm going to say U is equal to this thing. And so that means my du, I totally forgot about the dy here. Oh, I can actually do it. So my du is 2y, right? X squared is nothing because that's a constant. 2y dy. And so my dy here is du over 2y, right? And so I have bounds though. So when my y is equal to 0, my u... Oh, but then I have an x squared. What the... Oh, my u is x squared. That's funny. What? How does that change my bounds? Or it doesn't, right? Could be... Oh, that's the strategy. So I don't need to do that. I'm gonna switch it back anyways. I'm just making it clean and simple. So I got 6x of this. My y, u, du, dy, cancel. I get 6x, 0, 1, square root u, du, right? And then from there, or actually here I get 3x, funny enough. And then from there, I just evaluate this integral. So I get something like 3x. And then this is, I believe, u 1/2. So I add a 1. I get 2 over 3 u 3 over 2, 0, 1. Oh, so the thing is I don't have to, right? I almost forgot. When I'm evaluating a definite integral, I don't need to put it back to how it was because it's just a number anyway. And so, oh, wait a minute. I have to actually put it back, right? So I get 3x, 2 over 3, and then I put my thing back, x squared plus y squared. 3 over 2, 0 to 1. And then, or actually, wait. I could put the 3 here and then put the 2 here. So I get 2x. So here I get 2x. Then I put back my original function here. There we go. And then from there, let me just evaluate. So this is, if I put in a 0, or wait, if I put a 1, I would get x squared plus 1 of this thing. If I put in a 0, I would get x squared of this thing. And so that's just x cubed, right? Okay, and then from there, now I can integrate that thing from 0 to 1. Oh, that's a very messy integral. So we can, oh, we don't want to factor out that 2x. So here we have x squared minus 1, or plus 1, 3 over 2 minus x cubed. I actually want to put all of them here. Let me just do that, just to make it clean. 2x of this minus 2x to the 4th dx. Right, that's my integral. I could factor out my 2, so I got 2 of this thing. X of x squared plus 1, 3. This is x to the 4th dx. Now, I could do these one by one. This one's easy. This one is a bit weird. Oh, I could do a u sub here. Yeah, I could do a u sub. So we'll do it. Yeah, we're going to divide these integrals. So here, let me just do this. This thing, if I solve it, well, it's just going to be, let me do this. 2 of this integral dx minus this integral dx. Now let's solve for this first one. So that's the thing about integrals. You want to keep peeling off everything until we get it. So here I'm going to do a u sub. So u is equal to x squared plus 1, right? And then my derivative of that is 2u, or 2x, I mean. 2x dx. So dx is du over 2x. Do I change my bounds? Yeah, I do change my bounds here. So my u, when x is 0, that means my u is 1. When x is 1, that means my u is 2. So I have 1 to 2. And then this is my x, my u, 3 halves, u over 2x. I take out my x. Then from there I get 1/2, 1, 2. Oh, much cleaner, right? And then from there, here I have 1/2 of, I integrate this thing, so I get 2, oops, I add 3 halves, so 5 halves, so 2 over 5 of u, and I think this was 5 halves. And this is from 1 to 2. And then I can still simplify this. I could say 1/2 of this thing. 1 to 2. And then this is just, well, if I plug in my 2, 2 to the 5 halves, what's that? Oh, shoot. That's something. So this is this minus 1. And we're done. That's something. A number. Oh my goodness. Okay. Let me. Oh my goodness. I totally forgot about the other one. Wait. My bad. I was integrating this. I forgot the other one. So I'm done with this part. Now I do this. And this is just, okay, this one's an easier version. So this is x cubed over 3. This is 1/3, right? And so from there, I have 2 of 1 over 5 to 5 over 2 minus 1. So I have that minus 1/3. How do I simplify? So I get 2/5 of this minus 2 over 3. What else do I need to do? Let me see. Could I, if I multiply, oh, there's this thing, right? If I multiply an exponent by an exponent, I get this. So that means if I multiply each of these things, well, I actually just get 2 times this, so 1 plus 5 over 2, that's 7 halves. And then this is minus 2 over 5. And then I think this was 2 over 3. And I think I could change this 7 halves minus 2 over 5. And then this is 5. Oh, I can't do that. What the? What else can I do? He evaluated that very nicely, though. I would say he did it very nicely. Like, really, really nice. 4 square root 2 minus 1. Oh, How in the world did he do that? Oh, he did some magic or something. Wait, let me see. How, how in the world did you do that? 2 5 halves is the same as 5 to the 2, right? Or, my bad. I meant, wait. 2, 1. Oh, it's this one. This one that's the inner. 2 to the 5th is what? Is 32. 4 and 8. So this is what? 4 and 2. 2 times 2, that's 4 square root 2. Oh, look at that. Well, simplification. And so here, I actually got some nice things here. Yeah. So while this is 1/3, let me jot this down. This is the same as 1/2 or 1 to the 5th. Oh shoot, I have a 2 somewhere. I don't know where Oh, okay, so this is 4 square root 2 minus 1. And then that's it, right? And then for the second integral, it's 1/3. And so if I were to plug all of them in, I would get this. Right? Oh, crap. What happened now? What did I miss? Oh my goodness, I did 3. This is supposed to be 5. So this is 1/5. So this is 5. This is 5. Oh my goodness. Okay, and then from there I get that number. So I get 8 square root 2 minus 2 over 5 and then minus 4. So there we go. That's the answer. Had to fight it, get. Okay. Okay, let me just double check, see if I actually got it. Okay, yeah. Okay, so that's it for today's video. I hope you guys enjoyed, and I'll see you all in the next one.